This lesson is about the resource-efficient textile processes for functional and smart textiles and is part of the Hacktex virtual training materials. Hacktex is a project on innovative smart textiles and entrepreneurship which is co-funded by the European Union. The lesson covers the resource-efficient textile technologies for functional and smart textiles such as digital printing and spray technology. The content of the lesson is as below: digital printing including inkjet printing, and as an example of applying the technology, inkjet printing of enzymes is introduced. Valve jet printing and 3D printing on fabric are two more digital technique which is discussed. The last digital technology is spraying that can be used both for dyeing and functionalization of the fabrics. Digital printing. The first technology which is introduced in this lesson is inkjet printing. Digital inkjet printing technology offers new horizons to the advanced textile manufacturing sector, as it is a resource-efficient technology that consumes just enough materials and chemicals, with minimum waste production after the process. The flexibility it provides to the fashion sector plays a great role in adapting to the fast-changing trends of the markets nowadays. High-resolution prints, endless color choices, high-speed production and potential of industrialization with no minimum run length are few of the outstanding characteristics of this technology. The designs are created digitally via software that are connected to the print heads. This allows a significant reduction of production time, as well as reduces storage space and costs related to the stamps, stencils used in rotary and screen printing methods. This technology has been popular since 1970s, conducting printing directly from a digital-based image onto the textile. The technology ejects tiny drops of ink onto a substrate. In practice, the implementation of the technology is complex. It is resource-efficient process, uses the least amount of materials, water and energy. The color model which is used in digital inkjet printing is CMYK. The time required in the whole printing process with its preparation is significantly shorter than conventional printing of textiles. There are main inkjet printing systems which are continuous and drop-on-demand. The focus in this lesson is drop-on-demand, which mainly include thermal and piezoelectric printing systems. It is good to mention that the piezoelectric type has been used more than the thermal type, because the thermal type has limited inks options due to the heat. In the thermal system, the heat is used to force ink from the print head. The electrifying resistors behind the print nozzle, creating an intense heat that vaporizes the ink to explode onto the substrate. On the other hand, in the piezoelectric systems, piezoelectric elements, crystals or ceramics, are built behind the nozzles. When there is a need to print a pixel, an electrical charge is applied. These elements force precise amounts of ink onto the substrate by pressure. Digital inkjet printing on textiles offers various advantages and features. It enables the handling of variable data, utilizes a non-contact approach, is compatible with different inks and substrates, allows for multicolor printing based on the CMYK system, operates without moving parts, and provides high-speed printing capabilities depending on the resolution settings. These characteristics make digital inkjet printing a versatile and reliable option for producing vibrant and intricate designs on textiles. Digital inkjet printing comprises several main components that are crucial for the process and the quality of the prints produced. Compatibility between the components is crucial in digital inkjet printing to obtain good quality prints. The software needs to communicate effectively with the hardware and printhead, ensuring accurate control of ink deposition and positioning. The ink chemistry should be specifically formulated to match the textile being printed to achieve optimal color rendering and durability. Additionally, the textile structure and properties should be suitable for the printing process and ink absorption, allowing for vibrant prints. When all the components interact seamlessly, the result is high-quality prints with accurate colors, sharp details, and good wash and light fastness. In the field of textile functionalization, inkjet printing technology has shown promise for the application of complex materials such as enzymes. One example of this application is the inkjet printing of enzymes onto textiles to achieve biofunctionalization. This process involves using digital inkjet printers to deposit enzymes onto synthetic textiles, enhancing their properties and introducing new functionalities. The researchers investigated the biofunctionalization of synthetic textiles through the sequential inkjet printing of enzymes, specifically lysozyme and tyrosinase, onto polyamide fabric. One aspect of interest in the study was the antimicrobial activity of the printed fabrics. To evaluate this property, the growth of bacterial colonies on the fabrics was examined. In the figure, a red dot was used to represent the growth of a bacterial colony. The researchers observed that fabrics that were inkjet printed with enzymes exhibited a significantly lower number of bacterial colonies compared to fabrics without enzyme printing. This reduction in bacterial growth demonstrated the antibacterial efficacy of the inkjet printed fabrics. This application has implications for various fields, including healthcare, where the antibacterial properties of textiles can be beneficial in preventing the spread of infections. Valve jet printing is a type of inkjet printing technique that differs in terms of resolution and functionality. While inkjet printing typically offers higher resolution capabilities, valve jet printing is known for its lower resolution output. In valve jet printing, which falls under the category of drop-on-demand technology, the printing process is initiated by an electromagnet that activates a plunger. The plunger is responsible for opening and closing the nozzle, allowing ink droplets to be ejected onto the substrate. Unlike traditional inkjet printers that can have a large number of nozzles, valve jet printing systems usually have a smaller number of nozzles, and the drop size produced by this technique tends to be larger. Valve jet printing technology is often employed for printing on thick substrates, particularly in applications such as carpet printing. The integration of 3D printing technology with textiles has sparked a new era of innovation in the field of textile manufacturing. This groundbreaking approach, known as 3D printing on textiles, combines the versatility of additive manufacturing with the flexibility and functionality of textiles, creating exciting possibilities for design, customization, and functional enhancements. The world of 3D printing holds a wide range of technologies. At the highest level, there are three major categories for production of a 3D part, including forming, subtractive or additive manufacturing. In the forming, the material will be reshaped. In subtractive methods, as you can see in the figure, unwanted material will be removed from the 3D object with different methods like cutting or etching. In additive manufacturing, the 3D object will be formed by the layer-by-layer building process. The method begins with a 3D model designed with CAD software. This model then digitized and sliced into model layers with special software. Accordingly, 2D layers will be 3D printed into a 3D build. It is believed 3D printing on textiles can be one of the solutions to open up opportunities and fulfill the requirements of functional and smart textiles, such as cost and flexibility, as a more flexible technique. The workflow of the method begins with a CAD modeling, and then the design is given to 3D printer, and as you can see in the figure, you can have polymeric patterns on certain places of fabrics, for example, to integrate printed sensors and interconnections. 3D printing on textiles offers numerous advantages, including patterned and water, solvent-free functionalization, improved ecological footprint, high productivity, flexibility, cost-effectiveness, shorter time to market for textile innovations, adaptability to changing customer demands, and the ability to develop innovative products for functional and smart textiles. These benefits make 3D printing on textiles a promising technology with the potential to revolutionize the textile industry. 3D printed textiles present several challenges that need to be addressed to ensure their successful implementation in various applications. Some of the main challenges include durability, flexibility, and comfort. Various factors affect the properties of 3D printed textiles, and they must be carefully addressed to ensure desired performance. Ongoing research and development efforts focus on improving adhesion, tensile properties, bending and drape properties, washability, and abrasion resistance to unlock the full potential of 3D printed textiles. Spray technology is an innovative technology that can be applied for dyeing and functionalization of textiles. Textile dyeing is one of the most wasteful, and from a sustainability standpoint, questioned industries. The newly developed iMogo Dye Max spray dyeing line is the answer for everyone looking for a sustainable alternative process. The beauty of the story is that not only does the environment benefit from implementing the Dye Max, profitability and productivity will also be greatly improved through the dramatically reduced waste water volumes, the greatly reduced energy and chemistry consumption, and the increased production speed and consistent and predictable quality. The fabric passed through some spray cassettes that spray dye solution on the substrate. The combination of high-speed spray application with the special iMogo autoclave fixation step enables high output. The technology is used for most types of traditional dye classes and for high range of fiber types. In summary, digital printing and spray technology are resource-efficient technologies for textile printing and functionalization with minimum consumption of water and chemicals, and minimum waste production. These technologies overcomes many disadvantages of the conventional methods of textile dyeing, printing and functionalization with reduction of time and endless flexibility of designs to adapt to the changing fashion trends, and developing innovative smart and functional textiles. The elimination of metallic stencils used in conventional printing process reduces cost, time and storage needed in the digital printing process. The interest in these technologies is rapidly increasing due to their great potential in advanced textile manufacturing, and their capacity of overcoming many disadvantages of conventional printing and functionalization techniques.